Hello. Forces was the topic that everybody did. Every single student did the topic of forces um, in the last week. And I have, as usual, got the various booklets open. Um, if you have any questions from any of them, then please get them in early, preferably. Just remember to specify booklet one, two, or three, depending on which one you have in front of you for Key Stage 3. Right. Anybody got any questions yet from any of the booklet? Three, question four, we have received. Um, Please do send the whole mark scheme answer to the booklet because I want to double check all of my answers. Well, I'm not going to do what has just been requested regarding the answers for this booklet. But for one reason, this topic is not on your test this weekend. So, the topics on your test aren't, we did not mention forces as being a topic on the test this weekend. Um, all right. Every test, everybody in Newcastle at least has a test this weekend. Depending on where you are, it's later. If you're in Manchester, it'll be the weekend after. If you're in Leeds, it's during the week next week. But everybody in Newcastle, you will have it this weekend. Um, I can tell you it won't come up. I mean, I am certain we are because it wasn't in the list of topics I sent out earlier this week. Not earlier this week. I sent it out ages ago. 2 weeks ago, I believe we sent an email. I'll double check what I wrote. Um, I said the key stage three, biology, lungs and respiration, circulatory system, enzymes and digestion, disease, chemistry, bonding, neutralization, quantitative chemistry, physics, equations, electricity, waves, not forces, maths, fractions, decimals, area, volume, indices. What we said. Um, yeah, year eight test, question mark, question mark. Don't know what that means. Right, I'm going to start doing the homework questions. So, booklet three, question four, I'll do in order that they've been asked. Question four, that looks like it to me. Um, So, firstly, I will do a little bit of a recap of forces in general and the important parts that I think are necessary here. So, a power lifter lifts a 180 kilogram bar from the floor. Um, yes, an email was sent out about 2 weeks ago with all of the topics on the test. But I'll write them down for you now since you're here. You've got an advantage. But thing is, it doesn't really matter. It shouldn't really matter for you guys. And I say this all the time. I appreciate you might think differently. But given that the test is on topics that you have all had a lesson on in recent weeks and months, it should be relatively fresh anyway. That's what I always say to everybody. I will write down all the topics once I get through a few of these questions. So, well, I won't write it down. I'll just show you on the screen. Um, Booklet three, question four. Sorry, back to that. The first question says, use this equation to calculate the weight of the gravitation. I'm not going to answer that question. Nor am I going to answer the second question, probably, but we'll see. Oh, I have to do this, don't I? Right, okay, fine. It says, work out the weight of the bar. Weight is the mass, which they tell you in the question is 1,180 kilograms, times gravitational field strength, they tell you is 10. 180 times 10 is 1,800. That's the answer. Right, and then the next part says to calculate the work done. Now, to calculate work done, you need a force and a distance. This makes this a little bit harder because it's not as obvious. The distance is obviously 2.1. The force, though, you might wonder, where is it? Well, it's taken from the previous question because you needed a force of 1,800 newtons to sort of lift this thing. Um, so the force applied is the 1,800 that you take from the previous answer and then multiply it. Work done is a type of energy, which means that the answer is going to be in joules. I will get through all of the questions in order, don't worry. I will set a time limit on this soon in terms of when questions can be asked until. Um, Part C. At the end of the lift, the powerlifter is stationary above his head for 2 seconds. How much work does the powerlifter do on the bar during these 2 seconds? Look, work done is, as it says here, force times distance moved. If you are holding the bar stationary, not moving it, then you are timesing by zero. You are not doing any work. So you explain that the distance moved is zero. And that would be question 4. Done. Right, move on. 6D, booklet 2. Let's have a look at that. I think booklet 1 and 2 might have been quite similar. 6D. Um, okay, that's almost a weird question, isn't it? Gannets have pockets of air between their muscles and their skin. Suggest how this is a good adaptation for gannets when they hit the water at fast speeds. Okay. That's nothing to do with physics, but the answer to the question um, is that by having some air pockets is a bit like if you had like you're wearing some floats, basically, they can act as like a cushion. So they can cushion or protect them a little bit. So protection is fine. So when they hit the water at fast speeds, by having a little bit of an air gap, it creates like a little absorber kind of thing. So protection is enough for that. 6D done. Um, when is the year 8 test? Q6, 6D, booklet 2. I just did that, didn't I? Yeah. Keep going through question 7, 8, 9, 5, 6 in booklet 1. Yeah. Question 6, booklet 3. I'll just do that one, then I'll move on to booklet 1 after that. Question 6, booklet 3. Question 6. This shows 4 blocks of different materials floating on water. Which of the blocks has the smallest weight? Surely the smallest weight is the one that's highest up, I suppose, out of all of them, which is C, isn't it? Right, so that's C. Um, this shows a life buoy next to a deep swimming pool. Right. Weight equals mass times. Okay, this should be really easy questions, these ones. To work out weight, you do mass times gravitational field strength. Just times those two numbers together. That'll be it. When thrown into the water, it floats. The two forces acting on the life buoy are the weight of the life buoy and the upthrust. How big is the upthrust on the life buoy compared to the weight of the life buoy? They must be exactly the same. If something is floating, look, if that's the water and something is floating in the water, then it's got a downward force, but that must equal its upward force. Otherwise, it would be moving down or up, moving up, right? It's not, it's just staying still. So it would be the same in that situation. Write down the equation that links these. The answer is resultant force, and you do well to learn this now. Mass times acceleration. Okay. And then if you know this formula, this question becomes easy. So resultant force is 4, so I'm going to put 4 there. Mass is 2.5, so I'm going to put 2.5 there. Acceleration is what we're trying to work out. So from your maths skills, you should know that acceleration is 4 divided by 2.5, and you can work that out. Right. Right. At this point, just to be clear, at 7:24, um, I won't take any more questions from the booklets, just to be clear. Is that all right? 7C booklet 2. I'm going to do booklet 1 altogether, so I'll get this out of the way first. Question 5, booklet 3. I'm not doing that question. This is a bit harder now. Yeah, this is a bit harder. Right. Okay. I'll just tell you the answers here because you wouldn't have done this. If anybody asks another question, you're not going to get an answer to it. Um, I have just done some booklet 2 questions. If you have any specific questions, you can ask them. but I'll only take one or two. Um, the answer to the question is 13,800. That is quite a tricky question. It shouldn't really be in here, but it's moments are these things that you wouldn't have done yet. And then the formula here is moment equals force multiplied by distance. But I'm okay with that. Calculate the distance d marked on the diagram. Okay. What you would do here is you would say, if that is the formula, and I appreciate you didn't have the formula, so you wouldn't be able to do this. 13,800 equals force. The force in the question, it tells you, is 11,500 times distance. You would do this divided by this to get the answer. But yeah, I wouldn't expect you to know the answer to that question. So that's a good enough question. Um, I'm not. Oh wait, hang on. 7C booklet 2. Yeah, just ask it once. Got it. Got it. 7C booklet 2. I'll get to booklet 1 last, just to let you know. You guys, I'm nearly there. 7C. Two variables to keep the investigation fair, right? What are we doing here? We are dropping steel balls into the drain. So I guess we should use the same ball every time. Generally, with this fair test question, that you'll see this a lot, right? Then you essentially, if you do the same experiment many times, then there are certain things that should stay the same each time. If you're trying to sort of do this experiment to see how deep this ball goes in different materials or whatever, then you want to use the same ball every time. Otherwise, you use a heavier ball once and stuff. It's not going to be fair. So you should use the same ball. And then probably also the depth of the sand should stay the same because the thing we're changing is the the height from which we're dropping it from. So that's changing each time. But what should stay the same is how much sand there is and maybe the ball itself. So you'd say the ball should stay the same. So use the same ball and use maybe the same depth of sand, or same amount of sand. That would cover that. Right. I think that takes me back on to um, booklet 1 then. I might just do most of this one. So let's just do most of it together. So 6B booklet 3. Nope. I think I might have done that already. So that's not done. Right. I'm just doing question booklet 1. If you're here for booklet 2 and 3, I'm not doing any more now because I would like you to arrive earlier and ask the questions at the beginning. Is that right? Question 1 on here. The drawing shows a snow buggy being pulled by a sail. The buggy rests on 3 skis on the snow. Look at that, looks like fun. The drawing shows 4 forces. Draw a line from each force. Right, the weight of the buggy. Weight is something that always acts this direction. Always. Okay, so B has got to be that. The force pulling the buggy along, right? Isn't this pulling the buggy along? This direction there. That's the way we're going. So that's probably that. The friction between the skis and the snow. So friction always acts in the opposite direction to where we're moving. Um, yeah, I'm not doing any of other booklet 2 or 3 now, so I will ask you to arrive on time and then ask the question. That's all right. Um, yes, indeed, at 7:15, it's now 7:30. Yeah, correct. So, the friction always goes in the opposite direction. I might come back to it at the end, but I'm not doing it right now. The friction between the skis and the snow is always the opposite direction of what you're moving in. That will be C. Nope, not D, C. Should be that. Right, a scientist traveled 80 kilometers each day in the buggy. How many kilometers did he travel in 10 days? Surely 800, because you just multiply them. The buggy carried the scientist's food and equipment for the journey. The table shows how the total mass changed. Interesting. The buggy sank deeper into the snow at the start than at the end. Why? Isn't it heavier? I mean, surely if it's heavier, um, then it sinks more, doesn't it? It's heavier. Right. Question 1 in booklet 3. Let me just have a quick look what it is and decide if I'm going to do it. Maybe I'll come back to it. Right. The buggy rests on 3 skis instead of 3 wheels. Why are skis better than wheels for traveling on snow? So essentially, it's the same reason why I don't know, it's a weird example, this, but it's the same reason why ice skating might be quite difficult. Because the thing that you're standing on doesn't cover much of the ice. Do you see what I mean? Like if that's your, there's going to be a really bad diagram again. Right, if that's your shoe, then that ice skate thing, right, is like this really thin little thing that's on the ice. Whereas if that was bigger, imagine it was like a big sort of big circle, then it would be a bit easier because it would be more spread out because it spreads out your weight a little bit. And so that's why skis are better for traveling on snow because they spread out the weight a little bit more. So I think that would be probably what I would write. Just to clarify, the person who's asking those questions about number one, booklet three, if you could just change your thing so that we can see your name, because otherwise I don't tend to answer the question. Or just let me know who it is. Booklet two and three, no, because you need to have, presumably, if you have attempted all of the questions in booklet and the questions that you've done, then you would have asked them all at the beginning, because that's what you're supposed to do. So no, I'm not going to answer. I might go back to question one on booklet three that somebody has asked, just waiting for them to tell me who it is. But as I say, the purpose of this is not for you to do the homework while I am doing it. So if you arrive at 7:15 and say, I don't understand how to do questions four, five, six, seven, that'll be how it works. Otherwise, I feel like you might be looking at them there and then to do it. Well, I might be wrong. Please correct me if I'm wrong. Shay. No, I don't think that was it. You're not doing booklet three. Sorry, whoever asked question one, booklet three, that was somebody else. If you could let me know who it was. So, when a bigger sail is used, the buggy goes faster. Why does a bigger sail help the buggy go faster? Well, because I mean, there's a few different answers, but I think it catches more wind might be the best answer. It's the sort of same reason why a parachute is so big, because it's trying to stop you by catching more of the wind. So I would probably go with that. Um, Catches more wind. John attaches a ball to a spring. The diagram shows what happens. Before and after, fine. Which arrow shows the direction of the force of the ball on the spring? Surely it's down, right? That's the ball is pushing it down. Um, um, But the spring on the ball, the spring is effectively like pulling that ball up. So that's why that's got to be upwards. This shows three metal balls attached to identical springs. Which ball is the heaviest? B, surely. Um, because it hangs down the most or stretches the most. That's the kind of thing I would say for that question. Um, another three identical springs. He puts a cube in. Each cube has a different mass. The diagram below shows the springs before and after John added the cubes. Springs before adding the cubes, springs after adding the cubes. Um, oh, Q on top. Right. Okay. So fine. Which is the heaviest? Surely it's T this time because it sinks the most or it goes down the most would be what I would say there. Um, Right. Give a reason for this. The reason for this staying where it is because the backward force is the same. Well, the forces are the same, basically. The forces are balanced, would be enough, or the forces are the same. One's pulling in the same force as another one, right? It's going to stay where it is. They then do this. Now this number is bigger than this number, you see? Which way will it go? It's going to go in that direction because now we have a bigger force in that direction. I'm just doing all the booklet one, Shay, so don't worry. Later, the ribbon was to the left of point X as shown below. Why did the ribbon move towards the left? Well, presumably because the team on the left pulled harder. Team A now pulled harder than Team B. That's why it moved that way. Like a tug of war, it's just a simple tug of war. Team A pulled harder. Now Team A practices by pulling a rope tied to a tree. They first of all, why does the tree not move? What is the force of the tree on the rope? Right, when things are not moving, this is the main part of forces, right? When things are not moving, all of the forces are balanced, okay? So while these people are pulling with this force, if nothing is moving, there must be a force the other way of the same number. So that's the answer. Okay, so that's why, even though you can't see that, the tree is not literally pulling. It kind of is. That's why it's not moving. The pupils do not slip because there are a force between their shoes and the ground. That is called friction. The reason you don't slip or fall over is because of this thing called friction. There is less friction on ice, for example, which is why you're more likely to slip and fall over. Question 4 says this. Astronaut, A, B, C, D. Okay. Which direction will they move? Well, the only see how those two are the same. That means they're balanced, so you mo won't move left or right. But you see how this one's bigger than this one. That means you will move that way. The letter you have to say for some reason. So A. It's like awkward question. Then now what's going on? What will happen now? Well, this number is the same as this number, and this number is the same as this number. So I think that the astronaut will not move. So remain stationary or not move or float or nothing, basically any of those answers. Why? You want to say because the all the forces are balanced. That would be enough as an answer to that question. Now there's something else going on. Which way are we going now? Um, Draw an arrow to show the direction which he will move. Okay, so you see how this number is bigger than this number. That means he would move up, but also this number is bigger than this number. So he's going to move up, but also to the right, which means that I would draw an arrow going that way to show that he's sort of going to go that way. He's pushed that way. Um, right, on a plane and a flight, which represents air resistance? Air resistance is always sort of against you. So whichever way you're going, it's the opposite direction. So B. When the plane is flying at a constant height, which two forces must be balanced? Right, if you're not constant height means you're not going up or down. You're staying where you are. The only way that's possible is if the forces up and down are the same. So A and C. When the plane is flying at constant speed, which two forces? If you're flying at a constant speed, as in forwards, then your forward and backward forces must be the same. So it's B and D in that one. Just before takeoff, the plane is speeding up along the ground, which statement is true? Right. If you're speeding up, this is the thing that people I taught I might have mentioned, which is that when you're speeding up or getting faster, then one force is bigger than the other force. In this case, if you're getting faster, then D has to be bigger than B. That will make you get faster. I think that's the answer, isn't it? Yeah. Like that. And then just as it leaves the ground, okay, well, if you're just about to leave the ground, in other words, start flying, then doesn't A have to be bigger than C? Otherwise, how are you getting off the ground? A's got to be bigger than C for you to get off the ground. So I think that's why that's the answer. Sally pulls a sledge in the snow. Um, Draw an arrow to the direction of the force of the rope on the sledge. Let's make sure that I'm doing this right. Um, so something in that direction, basically. Direction of gravity is always down, always. Okay. And then force F is the friction between the sledge and the snow. Sally then pulled the sledge over a concrete path. Friction is less on snow than on concrete. Give a reason for this. Oof. I mean, it's snow's more slippery. I think that's what I would say. Which arrow, A, B, C, or D, show the direction of Joe's weight? Weight is always straight down. Weight, gravity, these things straight down. C. Which arrow shows the direction of the force of the rope on Joe? The rope is effectively pulling you up a little bit. That's why you're sort of hanging. And so A, based on this thing here. Sarah swings towards Joe. Sarah lets go of a trapeze and Joe catches her. What happens to the downward force on the rope of Joe's trapeze? Well, this is you've just what you've suddenly done is made yourself heavier because now you're holding another person, which means that this is going to push downwards more, isn't it? So surely it increases because the weight has increased. I think that's what I would say. Or there are two people now. There's two people there. That's my explanation. Joe lets go of the trapeze, and both Sarah and Joe fall safely below. What happens to the downward force on the rope when Joe lets go? Um, it decreases, doesn't it? Because look, right now, these people are pulling the rope downwards. When they let go of the rope, now that force is not there anymore. So it's decreased. That's what you want to say. Um, Tasha put okay. Right. Obviously, if you do this, it's going to move to the right. If they're the same, it will stay still. If this is bigger than this, it will move left. If this is now 8 altogether, and it's the same as this 8, so it will stay still. How do you measure forces? We use something called a Newton meter, which is this one here. It's called Newton meter. Newton meter. Because Newton is the unit of force. So it's a Newton meter. 9, Tommy's doing a bungee jump from a bridge. He's attached to one end of an elastic rope. What force makes him fall to the ground? Gravity does. He does not hit the river below the bridge. What makes him stop falling? Isn't it the rope? Is that the answer? You're doing a bungee jump. So, yeah, the rope. Okay. Um, Jill weighs less than Tom, so she weighs less. The rope will stretch less, won't it? If you weigh less, you don't stretch it as much, basically. I will do the couple of questions that people have asked, the new people, I've just asked in a moment. Um, Jill's dad watches her doing the bungee jump. He's standing along the bridge, shout bungee at the same time. Okay, this is wave suddenly. Why does Jill's dad see her before he hears her shout? This has nothing to do with forces, but it is science. Um, with a firework, when you see it explode or something like that, sometimes you then hear the noise later. It's because light travels faster than sound. That is the reason why we often see things before we hear them, because the sound takes longer to get to our ears than the light does to get to our eyes. Um, Tom is near Jill, the dad is far away. The shout will sound, if Tom is near Jill, it will sound louder, surely. And then the part of the ear is called the eardrum. I don't know why that's in here. Um, and that is the end of that. Right. Someone asked question 7, booklet 3. I've just got a couple of questions to do. The person again who asked for question 1 on booklet 3, if you just let me know who you are, that'd be nice. And 7, booklet 3. I might have done that. Oh no, I didn't. Right. The diagram shows how the thinking distance and the braking distance of a car add together to give the stopping distance. Okay, so a stopping distance is something that is basically how far you go before you stop, from when you see like a problem. There's two parts to it, something called thinking distance, something called braking distance. You might have done a bit of this in the lesson, depending on who taught you. Um, the stopping distance is found by adding the distance the car travels during the driver's reaction time, that's what thinking distance is, and the distance the car travels under the braking force. Okay. Which would not increase thinking distance. It's the tires that affects braking distance. And then part C, the braking distance, you can see as you get faster, the braking distance increases. That would be 1 mark. As you get faster, braking distance increases. But just as a little general tip for all of you, when you get these graph questions and it is not a straight line, it is a curve, you need to acknowledge and explain why it might be curved. What does the curve mean? What difference does it make if this was a straight line versus this being a curve? What's the curve's significance? The significance is that when something is curved, it is increasing more there than it is here. Do you see what I mean? See, that bit's like flatter, that bit's steeper. So you need to explain that at higher speeds, the braking distance increases more quickly. That would be the other mark. Okay. Oh my God. Right. Draw a line to show what will happen on an icy road. On an icy road at the same speed, your braking distance will be bigger. So I think you'd do something like that, just above it. And then I think I want to leave that because that's a bit of a comprehension question. Um, cathedral. Okay. Question 5, booklet 2. I'm not doing question 5, booklet 2. But I will finish with the booklet 1 from Key Stage 3 S3. Um, just to be clear, the person who made the comment about think you know what he said. I will be contacting your parents about it shortly. Um, so question three. Um, question one, booklet three. Let's do that. Um, um, Part of a bus route is along a high street. The distance time graph shows how far the bus traveled along the high street and how long it took. Right, a distance time graph. Um, just to confirm, sorry, just to confirm who asked this question. Just confirm who you are and that you're asking for question um, one from booklet three. I don't think anybody else has asked it, so I just want to make sure I'm explaining it to the right person. No? Okay, no one's telling me, so I don't need to do it. No, we have. Yeah, I say I'm not. If you've been asking questions since the beginning, I'm not going to answer questions now because I know that you are just doing it there and then. I'm not going to do that. Um, um, can you do two? Someone has asked. What booklet number is that? Is that booklet three? Have I done number two? Um, no, I don't think I need to do number two. Number two is quite. If it's the same booklet, it is booklet three, isn't it? So that should be quite straightforward. Um, just to be clear, going forward, I will only answer questions if you put your name after any comment. Because if I don't know you, like some people, I can see their names, but some people are here as an anonymous attendee and making comments. So I will answer questions if I know who it is that's asking them. Question two. Shouldn't really need to do that. The total force is those two added together. Should be easy enough, right? Um, then work done. You need a formula for this. So work. Oh God, how'd you do that? Total force is resultant force. Work done. You need a formula which is force times distance. So the distance is 80, and the force is the answer to this question. That will go into there, and you'll times them together. TDD. So just to be clear, with these questions, when does this end? Um, it doesn't matter. I mean, you can go, and I'm not keeping you there. Um, 6B booklet three. I think I've already done that. Yes, I have done 6B booklet three. There is a formula there. You need to just follow what the formula says. Okay, I've done that. Right, I think I've done everything. The person who again asked for number one, I'm just waiting for you to confirm who you are if you want me to do question one. If not, I guess you're okay with it from booklet three. It is not an easy question, I accept. Um, no, not going to do question five. Um, this is always being recorded. Yes, I think so. Did I remember to turn it on? I did. Yeah, it ends up on our YouTube page afterwards. Right, I'm not answering any more questions. As I say, reminder, um, do try to come at the beginning and ask all your questions at the beginning. I'm just all I don't want is for you guys to, and I appreciate not many people do this, but I really don't want you to sort of open up the booklet and be looking at it and asking questions as you're doing, as I'm here, which defeats the purpose really a little bit. So have a go at it before 7:15 p.m. on a Wednesday. Um, Write down the questions that you didn't know and then ask them at the beginning. That's the way I would like you to do it. Right, I'm going to return in 10 minutes to do the year 10 ones, if there are any questions from year 10 and year 11. Oh, yeah, sorry, I was going to give information on a test on Sunday. Apologies. Let me get the email out that I did, I promise you, send. I need to find a better way of communicating this, but I did send it. I did send it, I think about 2 weeks ago. Um, again, I wouldn't worry too much about the test in that it is topics you have done recently in the lessons. Um, so you will have some understanding of it. You have done homeworks on it. You have attended these things where I've done questions on it. Um, so, it's not anything to worry about too much. I'm just pulling up the topics. Give me a second. Right. Um, so, quite a lot of information here. I appreciate it. But key stage three, which is all you guys here. These things you have done in lessons recently. By recently, I mean I appreciate it's gone back a little while. Um, um, Yeah, I mean, look, we have to keep an eye on the test results a little bit, and if we feel that the group that you are in isn't the best for you, then we may consider a change, right? And that is obviously partly based on test results a little bit, right? We have to just think about you more than anything else. It is in your benefit. That's all we think. We think in your benefit. Don't think of it as a punishment, regardless of what happens. But lungs and respiration, I'll give you a little thought of what's in my head about some of these topics. Um, so, again, anonymous attendee who was just asked a question. I don't know who you are, so I really don't want to answer a question. So, lungs and respiration is to do with yeah, lungs and respiration. Yeah, make sure you know the equation for respiration. Circulatory system is all about the heart and blood vessels like arteries, veins, capillaries, you may have remembered. Enzymes and digestion is all to do with those enzymes called amylase, protease, lipase. Disease, you must have done quite recently when you learned about viruses and bacteria and vaccines. I would give you a heads up, make sure you know how a vaccine works. Chemistry, bonding, there won't be that much on that for you guys because it's quite a hard topic and it's slightly more GCSE stuff. Neutralization is acids and alkalis. Quantitative chemistry is when you had to find things like relative formula mass, like adding up some numbers. A lot of it is adding up some numbers, at least at your level. It later gets a bit more complicated. Physics, working with equations, as that's just in every physics topic, like you might have to do some equations stuff. Electricity, yeah, series and parallel circuits, and waves. You remember you did some stuff on waves. And then maths, yeah, that's what it is. Let me see what else anybody asked. Don't get area and volume another question. I struggle with it. I need help. Yeah, well, let's see how you do in the test, and then the thing with you guys with this stuff is that you I appreciate that you have just said to me that I struggle with area and volume, but the time for that shouldn't be just as a general tip. Let's try not to ask for help 4 days before the test is coming. If you know that you struggle on a topic, for example, then tell us in advance, tell us that you're struggling with this topic or you need some more stuff on this topic, as many people do, especially the year 10, year 11 group. You guys should get into that habit as well, rather than just when the test appears. But give it a go and we'll see how it goes. Yeah, if you I don't know what I was going to say there, but don't worry, it is not really hard. Just do it, and see how you do. Just remember the tests that we do are generally low pressure things. You get to see how whether you know it or not, and if you don't, you at least you know, and that's the main thing. Right. I think I'm going to just grab a coffee. What should I do to practice questions? My best advice for you is to go back over some previous homeworks that we have done, which you have been doing, obviously, if you've been here anyway, because a lot of questions do kind of get repeated in the tests a little bit. So that's probably my advice. I'm going to be back in 5 minutes to do the 10 year 11 stuff. Right. Hello. Yes, I shall open that up. Oh, have I got it ready? Um, okay, give me one moment. I don't know if I've got the right one open here. Okay. 7C, is that this one? This one? Yeah. Um, so, question 7C says the graph shows how the braking distance of the car changes with the speed of the car. The force applied to the brakes does not change. What conclusion can be made from the graph? So, first things first, what you can see from the graph is that as your speed increases, your braking distance increases. But as I said, it's the exact same question was in the year nine one actually. If you ever have to explain what is happening to a graph that is curved, you need to say what that curve means. Because if this had been a straight line, then your answer would still be the same, that as speed increases, braking distance increases. What's the curve got to do with it? The curve basically shows that at lower speeds, the braking distance increases more slowly, but at higher speeds, it increases more quickly. So, because that's why it's steeper there than it is there. So, first mark for saying as speed increases, braking distance increases. But the second mark is for interpreting what that curve means. The curve means that at lower speeds, or you can say the other way around, at higher speeds, the braking distance increases more quickly. Um, any other questions from this booklet? It's not, I don't think it was terribly hard, was it? Um, I think that might have been the same as the year nine one. That would be very similar. Okay, what I'll do while I'm waiting for people to ask questions, I will just do a little recap of the bit I find interesting about forces quickly, which is the bit about stopping distances. The stopping distance is imagine a car is traveling along and then you suddenly see in the distance, or not even in the distance, in the very near to you, someone suddenly run out in front of the road, and you realize you have to stop your car as quickly as possible. What will happen is your car will not stop immediately. It will continue going, and hopefully come to a stop before hitting the person. That distance that it travels is called the stopping distance. It is the distance your car travels, or bike, from the moment you see the hazard to the moment the car actually stops. How far you travel, it's a distance. That is made up, though, of two different parts, because from the moment you see this problem, the next thing you need to do is brake. But you're not going to be able to brake instantly, because we all have a bit of a reaction time. So during that time, your car will still be moving, and hopefully you will press the brakes around here. That distance that you have traveled between seeing the problem and getting to your brakes is called your thinking distance. Then once you press the brakes, you also don't just stop instantly. Your brakes slow you down. And as you're slowing down, you're still traveling. And then you'll come to a stop, hopefully there. The distance your car travels while braking is called your braking distance. So your stopping distance is made up of two different things. Um, Thinking distance and braking distance. You need to make sure you are comfortable with the different factors that affect those two things. Your thinking distance is affected by three main things: alcohol, drugs, because that slows your reactions down, tiredness or a lack of concentration, because that tends to increase your reaction time as well, and speed. Don't forget, speed is something that affects your thinking distance. Your braking distance is affected by your speed again, Your quality of your or condition of your tires. If they are old and worn out, they're more likely to skid. The condition of your brakes, if they are old as well, they're more likely to not work as well. And the last one is the road surface itself. If it's wet or icy, you are more likely to go further. Um, there was something else I was going to say about that. Any other questions at all? Drastic questions from this booklet that anybody has not asked yet? I think it's quite an easy one. I think that's why there's not many. Although that might not be. There's a second part to 7C, is there? Oh, yeah. As in, oh, I see. Right, so I've done the first part. Yeah, okay. Let's read it. Firstly, draw a line on the graph to show what is likely to happen to the braking distance at different speeds if the car was driven on an icy road. If you're driving on an icy road at the same speed, it's a good thing I just mentioned this, at the same speed, isn't your braking distance going to be bigger? So without the ice, this is your braking distance at 5 miles an hour or meters per second. But with ice, it's going to be further. So basically, you need to draw another line where everything's above where it is now, essentially. That's what you need to do. So draw a line that's to the left of it. But make sure it starts at the same place because your speed is zero, your braking distance is zero. What else did it say? The local council has reduced the speed limit from 30 miles an hour to 20 miles an hour on a few roads. The reason was to reduce the number of accidents because, as we just explained, reducing your speed has an effect on both your thinking distance and your braking distance, so it has a big effect on your overall stopping distance. The councillor said it will be much safer because drivers can react much faster when driving at 20 miles an hour when driving at 30 miles an hour. This statement is wrong. Yes, it is. Your reaction time is not affected by how fast you are going. Your thinking distance is affected by how fast you are going. Your reaction time is what it is. It's not affected by how fast you're going. How do I put that into words? I don't know. So it's just testing. It's a very common misconception here, which is the difference between um, reaction time and thinking distance. I think people do get a little bit confused by that, which I understand. Um, yeah, so that's the answer. Reaction time does not depend on the speed of the car. The local council must decide whether to introduce the lower speed limit on a lot more roads. What evidence should the local council collect to help make the decision? Jeez. Um, so they need to decide. So on this road, so on these few roads, they need to look at the data and see how many accidents there were before the speed limit change and how many there were after. That will help them decide if they should now introduce that on a lot more roads. If it didn't make any difference on the few roads, why would you do it on all of the roads? So you need to have a look at the data. How many accidents were there before you changed the speed limit on these roads, and how many were there after? Right, I want to put a question down to see if anybody knows the answer to this, which is imagine that at a particular speed, well, in fact, let's make this up. Let's pretend that at 10 meters per second, I'm making up these numbers, by the way, my thinking distance is 4 meters and my braking distance is 9 meters. I'm making that up completely. Let's pretend I'm now going at 20 meters per second. You want to tell me what numbers you think go in there? So if at 10 meters per second, my thinking distance is 4 meters, what is my thinking distance at 20 meters per second at twice the speed? What is my braking distance at twice the speed? 8 and 18 are the answers from anonymous attendee. 8 and 18 are the answers so far. Um, one of those is correct. One of those is not correct. Your think 4 and 18. No, that's not correct either. Okay, so the thinking distance does correlate with your oh, there's more answers. 8.89. 8.9. No. Your braking distance has to increase because you are going twice as fast, right? It has to increase. Both of them have to increase, just to be clear. It's just by how much they increase. So your thinking distance does follow. Yes. No, the 8 is correct. It's the 18 that's wrong. Um, so I'm explaining. Right. Your thinking distance does follow what you expect it to be. So if you're going twice as fast, so we have times this by 2, your thinking distance also doubles, right? Again, I made up the 4 and the 9, but the doubling is the same, if that makes sense, right? So it would be 8 meters. If it was 4 at 10 meters per second, it would be 8. But it's not. Anybody else? Yeah. It is not 18 when you are going twice as fast for braking distance. Let me explain why. I will do a few minutes on electrolysis. I'll do one electrolysis in response to that question. Um, so the braking distance explanation is as follows, and it links to another physics topic, which is why I think it's really important to know this. What your brakes do ultimately is is stop you, right? But if something is moving, it's got kinetic energy. What the brakes want to do is get rid of all of that kinetic energy. That's what they want to do. They want to bring it down to zero. The way they do it is by pressing against your wheels and getting hot. So the energy conversion is kinetic energy to heat energy, usually. That's what happens. But what we're trying to do is get loads of kinetic energy brought down to zero. That's when you've stopped. That is what your brakes are doing. So what we're going to do is use the formula for kinetic energy, which is a half times mass times speed, velocity squared. Okay. Now I'm going to pretend, just for the sake of this illustration, that we have a 1 kilogram car. Okay. Just both of these in both situations. What we're going to do is work out the kinetic energy of the vehicle when it's going at 10 meters per second and when it's going at 20 meters per second. Okay. If it's going at 10 meters per second, the calculation would be a half times mass, which I've said is 1, times its speed, which is 10, squared. 10 squared is 100. 100 times 1 times a half is 50 joules of kinetic energy. So that car, traveling at 10 meters per second, has 50 joules of kinetic energy, which your brakes have to get rid of. Okay? At 20 meters per second, the calculation is a half times 1 times 20 squared. 20 squared is 400. 400 times 1 times a half is 200. At 20 meters per second, your brakes have got 200 joules of energy that they're trying to get rid of to stop your car. The key point is that when you are going twice as fast, you have 4 times as much kinetic energy, which means that your braking distance will be 4 times bigger than it was before. Try to remember that. It is a important little thing, which is your braking distance doesn't just double or triple. It doesn't go with the speed. It goes with the difference squared. So not 2, but 2 squared. If it had been tripled here, then it would have been 9 times bigger. You sort of square the multiplier, as it were. Right, that was it. I thought that was a nice little illustration to do. Right, given that nobody's asking any more questions on the homeworks, I think they must have been relatively okay then, given that nobody's asking any. Um, what's a system? Um, it's hard to explain. I mean, it depends. In chemistry, it can be just a closed container. It means that nothing can get in or out of it. That's essentially why a system is used. If you have a closed system, is often used in chemistry to illustrate that. In physics, it can. Got a chat going. Oh God, more questions. 3D in the year 10. Okay, I'll come to that. It's in 2C. Oh, sorry. Let me just answer the other question that just came in. 3D in year 10, because there's a new student, I believe. Welcome. Um, right, let's talk about 3D for a moment. Do we have our homework and notes due this week, or do we have time? I don't know the answer to that question. I would say that you shouldn't need to do your homework and notes for this weekend. And yeah, for everybody that's here, if you haven't done your notes and homework for this weekend, just say that I said it on here and you do it for the week after, given that you have a test this weekend. Um, 3D, right. I need to read all of three quickly. The drag lift, arrows of force, pulling up, normal contact force. C is easy. 3D, at the top of the slope, the skier leaves the drag lift and skis back to the bottom of the slope. This shows the velocity as it moves. After 50 seconds, the skier starts to slow down. They decelerate at a constant rate, coming to a stop in 15 seconds is easy. Right. If 50 seconds have passed, right, we're going to stop, right? The only way you stop on one of these graphs is when the line comes back to the beginning, because that's when your speed is zero. So it says it took 15 seconds for you to stop. So if we're on 50, then we need to be on 65 when we stop. So you need to draw a straight line, use a ruler, that goes from there to there where it's at 65. So it's a 15 seconds stop. That's it. Okay, and then oh, oh, uh, exam topics. Yeah, in a second. 2C. Let me have a look at that. Um, um, I would have. Well, I'll check the answer. But I would have said. I would have said the first one. Let me check. Cool. A group of objects that interact. So it's a very long way of getting there. Yeah, it's just the only one that makes sense. Yeah, that's what a system is. Okay. Um, exam topics are first of Feb. Right. Here they are for everybody is here, hopefully. Um, these are all things you have done recently, so don't stress about it too much. Just do a test, see how you do. See what you know, see what you don't know. That's the whole purpose of all the tests that you do at the moment. Find out what you know and what you don't know. That's it. Um, all right. Okay. I will, given that there are no further questions, at least for now. Um, oh yeah, I will. What shall I do? Yeah. Okay. I will just talk through these quickly and tell you the kind of things that I would expect you to. Um, yeah. So if you're in Leeds, then it's next week. If you are in Newcastle, it's this weekend. That's the way. And if you're in Manchester, it's next week as well. Just a little bit complicated timing wise. Um, yeah. So, what was I going to say? I was going to say things like lungs and respiration. Um, key things that I would recommend you know. Key. Yeah, I don't know what's on the test, just to be clear. I can't remember what's on the test. But I'm just telling you that when I think of these topics, the things I think of are obviously equation for respiration, the fact that respiration releases energy, the fact that that happens in the mitochondria, the adaptations of the alveoli, which is a very common question, which is like that they have a large surface area, which speeds up diffusion. They have thin walls, which speeds up diffusion. They have a good blood supply, which results in what's the word I'm looking for? Maintaining the concentration gradient of diffusion. Circulatory system is all about the heart and the whole arteries, veins, capillaries, the bits of the heart like the vena cava and that stuff, right? Components of the blood, plasma, white blood cells, red blood cells, enzymes and digestion. Just make sure you know that table. There's a table which has three enzymes, what they each do in terms of what they break down, what they break it down into, and where they're found. That is fundamental in understanding or getting digestion questions right. Disease, you did it. Make sure you know how a vaccination works. Bonding in chemistry, covalent ionic bonding, know the differences. Neutralization, probably really just acid and alkalis pH scale. Quantitative chemistry is tricky because it's, yeah, it's a bit harder topic. Energy and physics, fossil fuels, burning them, that stuff. Electricity is what it is. Waves, electromagnetic spectrum, like what microwaves do and stuff like that. That stuff. Maths, can't really talk about it. Just, yeah. For year 11, animal and plant hormones is mostly the menstrual cycle and the function of things like FSH, LH, estrogen, progesterone. Genetics A and B is to do with those genetic disorders, and you have those allele diagrams with the two letters, and you stick them in the right places and do stuff like that. Genetics B, there's things like evolution and selective breeding. Chemistry, redox electrolysis. I'm going to do just something on that in a second. Quantitative chemistry, again, same thing. Analytical chemistry, know the gas tests. Test for hydrogen, oxygen, carbon dioxide, and I don't know what I missed. Chlorine. Physics, electromagnetism, fine. Okay, that's what it is. Right, I'm going to finish with um, just something on electrolysis. Two electrolyses I will do. Um, There's a question. Timing. Okay, thank you. No problem. Um, I'm going to do two electrolyses. The electrolysis of molten aluminium oxide, I'm going to explain now. Okay, in electrolysis, the word here is extremely important because if it said aluminium oxide solution or aqueous aluminium oxide, it completely changes the electrolysis. So you must understand why that makes a difference. The reason it makes a difference is because when you melt this compound, the only thing in it are the ions, the positive ion from this and the negative ion from the oxygen. Aluminium is in group 3. That's why I know it's a 3 plus ion. Oxygen is in group 6. That's why I know it's an O2 minus ion. You should know these things. There we go. Um, yeah, I know you forgot your horse's homework because I actually sent an email to say you'd um, forgotten your horse's homework. Yes, you can take it next lesson. Um, 3D on the year 10 forces booklets. Okay, I will come back to it in a second. Um, right. In this electrolysis, this is how it looks. Positive, I'll just do this one, then I'll do that question, then I'll come back to the other one. In the solution, the electrolyte, we call it, we have these ions, positive and negative ions. Um, During this electrolysis, the whole point of electrolysis is trying to split up a compound back to what you started with, sort of. With aluminium oxide, what was going to happen is that these positive ions will be attracted to the negative electrode, and these negative ions will be attracted to the positive electrode. We will get aluminium coming off here, and we will get oxygen coming off here. That is essentially it. That is the electrolysis. There are these things called half equations that I'm not going to go into in too much detail for now, but it is important to try and understand what's going on here. A positive ion became a positive ion by losing 3 electrons. Now it's getting them back, so it goes back to what it was to begin with. Sort of similarly, a negative ion gains 2 electrons to become negative, so it's now going to lose them again to go back to what it was started with. But with this one, you have to balance things out, and it gets a bit awkward. So that's the half equation for that one. Right, why there's so many comments? Um, Sorry, someone asked me about electrolysis. This has nothing to do with the test that's coming up. Just so you understand it. It's nothing to do with our test coming up. Um, so yeah, just to be clear, the reason I'm doing this is because someone has asked me a question about electrolysis, and the people in year 11 are doing electrolysis on their test. If you're in year 10, you are not. But yeah, just so you understand, I don't know what the question is. Um, yes, and people in year 11 have got electrolysis on the test that we are doing. There. Again, what's your question regarding that? Why would we do it on exam 2? I don't know what that means. I mean, what we do here is nothing to do with the paper 1, paper 2 stuff that you have in your end of year exams. We're testing you on a few topics after we have done them. And we did electrolysis quite recently, so we're testing you on it now. That's how we do it. We don't directly follow what's on your paper 1 and what's on your paper 2. Yeah, because we have a third one, and we have a third one in April. So yeah, that's just what we've done recently, done since then. Right. I'm not going to do the electrolysis and batteries thing. That is a slightly different topic. It's all fuel cells. It's how a battery works, basically. Okay. But I'm not going to be able to go into that. I need to answer some of the homework questions. Um, so, how many times will we do each new topic? I don't know what that means again. We tend to do each topic once, generally, until we get to the end and we do loads of revision. So we just need to get through all the topics. If we've done electron, we've done by about March time, we will have done all of the topics, maybe even February. March time, we'll have done all of the topics that we're going to do in our normal lessons. That doesn't mean that every single little thing has been covered. Like fuel cells would be an example we might not have done that much of, but we will get to it as we do practice questions in the months leading up to your exams. There are a couple of topics we do more than once, like electromagnetism and forces we did in year 10 as well. Electrolysis we didn't do before, but we try and get through it all. And also, don't forget, for those of you in year 11, the advantage that you have over everybody else is that from the 1st of May, I will be available here every single day for any questions that you have in the lead up to your exams every day for 6 weeks. Um, so any questions that you have last minute and stuff, I will be there. Um, Oh yeah, sorry, yes. So basically, the way we did it, yes, that's a good question actually. Generally, we do the sort of paper one stuff, the first sort of year 10 topics. We do several times throughout year 7, 8, 9, 10 because they're just a bit easier. And then there's certain topics we just leave for year 11, like electrolysis, like homeostasis and so on. So we won't be doing those again in terms of a topic, but all you're going to be doing for the next few months is loads of exam papers and revision, and it'll all just come back then. So don't worry. Don't worry. Um, what am I doing? I need to answer that year homework, don't I? 3D, year 10. Oh, I did. That was it, wasn't it? It was this one. There's the answer to it, just so you know. So you had to bring the graph down to 0, but 15 seconds later from where it was. So it was on 50, 15 seconds later at 65, so it comes in. Um, okay, 5D year 10. Um, Whoever that is, you need to tell me who you are. I'm not going to answer a question to a bunch of letters. Okay, you're not answering, so I think I might just end it soon. Um, okay, I will do one more thing again for the mainly for the year 11 benefits here, which is that was an electrolysis there. The most common electrolysis, and it's usually a required practical in most exam boards, is the electrolysis of sodium chloride solution as well. So the crucial thing is that when you have solution, there are two more ions to think about, H plus and OH minus ions. Sodium is Na plus, chlorine is Cl minus. There are now four ions here, unlike the previous one when it was molten, there's only two. And when there's only two, it's fairly obvious what will happen. The positive goes one way, the negative goes the other. But when there's four, there are more complications involved, right? Oops. Because you've got two positive ions. How do you know which of those two will go to the negative electrode? The answer is the less reactive one. In this case, hydrogen is less reactive than sodium, so we get hydrogen being produced over here. The sodium stays there. What about the two negative ions? Because we've got Cl minus and OH minus in here. Which of those two goes? Well, the explanation is a bit weird for this one. It is that if you have a group 7 ion, that is the one that will go to here, and you'll get chlorine coming off here, and that will stay here. If that had been a different ion, some other one like, oh God, I don't know, something else, then OH minus would be the ion that goes to the electrode. Um, right. I think that's probably it. So nobody's asking any more questions. Um, Oh yeah, there's a third product actually, I should have said. Because these get left inside the solution here, we end up with something called sodium hydroxide as well. There are three products of this electrolysis. I won't do the half equations, but that is the understanding of the electrolysis, at least quite quickly. Um, yeah, so again, as a reminder, anything you are if you're in year 11 at least for now, anything you are unsure of, or anything you feel that we haven't quite got round to in the lesson. Remember, we are trying to cover four subjects in 2 hours a week. So there is chances are that we might not have done everything, but I will be available to answer everything and go through everything. So as I say, you effectively get, I don't know what it is. It's usually for about 6 weeks. I'm usually online for 30 minutes to an hour every day. So what, 6 weeks? Six, seven, six, that's 42 times. That's 42 hours. Yeah, there'll be quite a lot of hours potentially during your exam period between May and mid-June that I will be here to um, just answer anything you need for maths, biology, chemistry, or physics. So don't worry. And same for those of you in year 10 for next year. Stick around. Right. Given that nobody's asking any more questions, I think I'm going to leave it there for today. And if you do have any other questions, then feel free to ask me. Somebody has a 3D in the year 10 paper. Let me just go back to that and see if I've done that. I did. That was 3D, and you asked for 5D as well, which I think I. Oh no, I didn't do 5D. Right. Okay, let me do that. Last thing, and this applies actually for those of you who are doing triple. There's a topic called moments, which you might not have got around to in the lesson again. So I will just talk briefly about it now. Use this equation: work done equals force times distance. So that times that is the answer to that question, which is fairly straightforward. Um, then, right, moments. The best way to explain moments is to think of a seesaw. Here is a seesaw, and there's two people sitting on the seesaw. Okay, right. Okay. And imagine it is balanced right now, as in they are hovering where they are. Nobody's down, nobody's up. Okay. The only way that's possible is if the force in this direction is the same as the force in that direction. Now, you'll notice that I deliberately drew a curved arrow here when I said force, because that's kind of what's going on, right? This is like the middle of a clock. It's called a pivot. And so it's not just going straight down, it's kind of would be curving around like a clock. We call that not a force, we call it a moment, because a moment is essentially a turning force. So it is not just about the force in one down, it turns, right? And moments can be clockwise or anti-clockwise. I should be able to figure out why now, because we have something going that way, that is clockwise, and something going this way is anti-clockwise. In order for these two things to not be moving, those two moments must be exactly the same. If one is bigger than the other, then somebody sinks, as it were. So the when do we do the topics in year 10? You said we would do them in year 10. We're doing the same thing in year 10. Fine. Well, tell me what you need, and then we will get through it. It's just that there's a big topic, so it's for different people. It's necessary to revise stuff, basically. So, I'm doing some of it now for that reason. This is a topic that you probably didn't get to in the lesson, but it is moments. Here it is. So, the that is what a moment is, okay? Now, if something is balanced, then the anti-clockwise moment will equal the clockwise moment. They have to be the same, just like any forces, right? They're kind of the same thing. So in this question, it says that the weight of the crate, where's the weight of the crate? There, causes a clockwise moment. So think of it like that way, as if it's going to fall down that way of this number. The weight of the forklift truck and driver causes an anti-clockwise moment. So because of these two, there is a anti-clockwise one. I think it's got anti-clockwise that way, isn't it? I got that wrong earlier, didn't I? Anyway, it doesn't matter. What is the minimum size of the anti-clockwise moment needed so that the forklift truck does not topple over? Not toppling over means it does not move. And so the moments have to be the same, just as forces have to be the same when things don't move. It is 13,800. The formula, which you of course get given, all of you, is that the moment equals force times distance. Let me explain. If this person is sitting closer to the pivot there, then they will provide a bigger moment. It's more likely to go down, right? The closer you get to, sorry, I got that wrong. If you get further away, sorry, so if that was longer and you sat right at the edge here, you're more likely to go down here than you are if you're closer to the middle. The further away you get from a pivot, the bigger the force becomes. Um, and so there are questions that we will look at where you have to do some calculations involving the moments. Um, yeah, momentum, levers, gears, don't worry. These are very short topics. The key thing is, I think sometimes with triple science, we can sometimes overthink those topics. The 80% of your exam is still the same topics. Your exam, when you do triple science, the triple science content in the exam is very small, like it is. So, but the other content you need to know better than someone doing combined science. That's the difference. You have to know it and be able to apply it better. So I do think you can easily get bogged down into these little few extra topics without focusing on the bit that's really important. So don't worry, it'll all be done. This is not a complicated thing. And as I said, all these extra sessions that I do is for this purpose, is to make sure that you are comfortable with every single bit of it. Calculate the distance mark D on the diagram. Well, we know the moment is 13,800. We know the force is 11,500. And then you can work out the distance by dividing that by that, essentially. Right, last thing I'll do. 7C year 10. Have I done that? No. Don't know who that is, but it's okay. Um, Newton's laws. Yeah, I'll do that now. Um, 7C part, that's 7C. Oh, I've explained this a couple of times. You might have to go back and watch the video, but I've explained that twice. Right, just on the laws, let me just finish with this. So, just because I appreciate it. The laws again are, oh man, what's happening? Less complicated than I think people realize. I mean, the first law, Newton's first law, is that if you have an object and the forces are equal on it, like so, then there's two possibilities. Either it's not moving, or it is moving and it is moving at a constant speed. That is essentially the law. I will open the textbook to prove this, because again, it is one of these things that I think gets overly complicated. Dum, dum, dum. So, forces, Newton's laws, somewhere in here. So, zero resultant force, which is what I just showed you here. That is a zero resultant force. Resultant force is the force in one direction minus the force in the other direction, effectively. When there is a zero resultant force on an object, again, there's two possibilities. If it's already stationary, so it's already not moving, it continues to stay stationary. However, if it is already moving, then it continues to move at the same speed, constant speed. So that first law is in two pieces, I suppose, which is that if something's not moving, it stays not moving. And if something is already moving, it continues to move, but at a constant speed. It doesn't get faster, it doesn't get slower if the resultant force is zero. So the forces are balanced on it. And then basically the second law now is going to be, well, what if this number changes? If one number is bigger than the other, and therefore there is a resultant force, in this case 20 take away 10 is 10, when there is a resultant force on the object, it accelerates. It gets faster. It doesn't just move to the right. Yes, in this case, you're moving to the right. Get rid of that because it's not true. Moving to the right, but you're now getting faster to the right. That is the crucial bit of this, is understanding the relationship between resultant force and what happens to your speed. In this case, your speed goes up. You are getting faster. Hopefully, that's what it'll say in a second. Um, Second law is basically this. Oh, yeah. So you're getting faster, and therefore you can calculate how much you're getting faster by. So in this particular case, if this object is, I don't know, 20 kg, and I have told you that this is the resultant force, we know it's accelerating. So can we work out the acceleration? Well, there's a formula, F equals ma, that says resultant force equals mass times acceleration. In this case, the acceleration is 10 divided by 20, which is a half. That is the second law. The second law is essentially the formula F equals ma. That's it. And it gets bigger if you're heavier and if the resultant force is bigger. And then the third one, well, this is the same thing actually. It's the same formula rearranged. The third thing is oh God, the required practical. We're doing that very soon. That'll be fun. Because you'll have all the required practicals coming up in the next few lessons for year 11s. And then the third one is when two objects interact, the forces they exert on each other are equal and opposite. So this illustration I used lots for those people I taught, which was if there is a person standing on the table, they have a weight downwards due to gravity. Because they're not moving, there is an equal and opposite force in the other direction. Um, and that also applies when you're pushing against a wall. There is an equal and opposite force in, well, equal and opposite implies the other direction. If you push something, say a shopping trolley, the trolley will push back against you just as hard. Essentially, that's what's going on. There is an equal and opposite force. And that's the third law, really. And then equilibrium is just when things aren't moving. So the crucial thing is the first couple, which is just where formulas come from. Right. I think that's it for now. As I say, especially for you and you guys in year 11, as we progress over the coming weeks, I will possibly extend these sessions a little bit for any other stuff that you need, because I am conscious that you will. But for now, I think that's it. So I will see you guys next week and enjoy your test. For those of you in Newcastle. Bye.